Good morning, everyone. I hope everyone is having a great weather, just like we have in London today. Well, so I'm Emir Demirel, or QMUL1. That's my barcode within MIP-Frontiers project. I'm doing my PhD in Queen Mary University of London. And my research is supervised by Professor Simon Dixon from Center for Digital Music and Professor Sven Albach from Doremir Music Research AB from Stockholm, Sweden. And I will be talking about my PhD thesis, which I give the title, Deep Neural Networks for Automatic Lyrics Transcription. And first I will talk about my motivation, why I chose this title. Then we will define the problem. And then we'll go through the state-of-the-art methods that attempted to solve this problem. And then in the automatic lyrics transcription chapter, we will go through our contributions in this research field. And finally, we will finish with summarization of our contributions and the outcome of this research. Hopefully, if you have time, we will have some demonstration. So this was my original thesis proposal, representations and models for singing voice transcription. So in general, automatic music transcribers were mostly modeling singing voice by means of pitch versus time. But obviously, there are other aspects in singing voice that are useful for defining the performance, such as vocal qualities, styles, note transitions, intonations, and last but not least, lyrics. As lyrics is one of the essential building blocks for the understanding, appreciation, and representing singing voice performances, we thought that this would be an essential feature for a potential automatic music transcription application. An example you see here, this is our research outcome. This is a commercial application developed by Doremir, but I will come back to that later on. So just to give an idea that we were actually built something that works. So let's define the task. That's my definition. The task of automatic lyrics transcription can be defined as the procedure of transforming a singing voice performance with lyrics that has a finite length audio signal into a string of text which is targeted to match that of the original lyrics or what humans would generate. So in mathematical terms, we can summarize this problem with this equation, which is predicting the likeliest word sequence noted by W here, given the acoustic features or observations noted by X, which is the fundamental equation for speech recognition. So when we apply this into singing data, this can be easily translated to automatic lyrics transcriptions. This lovely equation is the thing that we're trying to solve. From the perspective of speech recognition, there are two major streams of approaches in the state-of-the-art. So the first one is the DNN-HMM based, the other one is the end-to-end based models. The DNN-HMM based models are composed of multiple independent computational blocks that build the overall word classifier, whereas end-to-end models provide a single module that is purely consisting of neural networks. Specifically for the DNN-HMM models, they use this concept called phonemes, which are the basic units of speech, as also Killian mentioned in his presentation. Words are considered to be consisting of sequences of phonemes. So first we have this acoustic model that learns a mapping between acoustic observations and phonemes. And phonemes or phoneme probabilities are converted to word probabilities using a pronunciation model. An example is given on the right-hand side. And to obtain more grammatically sensible outputs, we smooth out the word probabilities with a language model. After we obtain the word probabilities, we obtain such a graph. This graph stores all the alternative transcriptions. So we apply decoding from left to right to obtain the final transcriptions, and this can be applied using the traditional algorithms such as beam search, Viterbi, etc. And then the state-of-the-art training approach is called sequence discriminative training, which uses maximum mutual information as the objective function. It is quite a spicy formula, so I didn't include that in this slide to avoid any kind of distractions. If you'd like to learn more about that, feel free to check the reference. In principle, this is like CTC optimization, if anyone is familiar with that function. So basically, the optimization is done on the sequence level rather than frame level. So as I said, end-to-end models, on the other hand, they are purely consisting of neural networks. They don't require a pronunciation model, as you see here. Because of that, we don't need prior human or linguistic expertise, which makes them really attractive, in fact. Specifically, sequence-to-sequence structures are very popular in the context of speech recognition, where the audio acoustic features are first encoded into a latent space that is usually referred as context vector, and then this context vector is then decoded into output transcriptions with a decoder network. And you can use CTC or attention as the middle block, but I'm not going to go into details of that. And most recently, transformers were introduced, which was considered to be a breakthrough in deep learning research, because they made CNNs and RNNs redundant according to this scheme. They are purely based on self-attached and fully connected layers, and due to that, they have fewer trainable parameters. They are parallelizable, unlike RNNs, and because of that, they come with faster training option. And on the other hand, the state-of-the-art end-to-end speech recognition system is also based on the transformer architecture. This is the literature review that will be useful to understand the following context. So let's talk about something more interesting. Let's transition from speech data to singing data. When we were conducting our research, we have oriented our progression based on the research questions that are displayed in the slide. What is the performance ceiling for lyrics transcription when directly adapting the state-of-the-art speech recognition to singing data? Most of the times, words are pronounced differently in singing compared to speech. So what are these systematic or common pronunciation variances, and how do they affect overall word recognition performance? Also, in our research, we observed that lyrics transcribers that are trained on a cappella recordings perform absolutely poorly on polyphonic recordings. And the vice versa scenario is also valid. Polyphonic models perform quite poorly on a cappella recordings. So we also asked, is it possible to obtain a single acoustic model where the performance is undisturbed across varying domains? And finally, one of the hottest questions in deep learning research, which one is better, DNN-HMM or end-to-end models? We are trying to answer that question as well. In our first publication, it was concerned with the first research question that we were tackling in. We used the state-of-the-art DNN-HMM speech recognition framework trained on the DAMP dataset, which is the benchmark training dataset used in lyrics transcription that consists of only monophonic recordings. We developed a self-attachment-based novel acoustic model, and we exploited neural networks for also building the language models. And then we were able to obtain 5% absolute word error rate improvement compared to the previous results. So word error rate is the standard metric to evaluate lyrics or speech recognition systems. And all in all, the shorter the better. So it's an error rate, basically. In our next publication, we applied a comparative study on the phonetic variances in word pronunciations between their canonical forms and in singing. In broader terms, we have observed that, well, no surprise, words are uttered with longer vowels, and also there were certain consonants that were omitted if they were supposed to be pronounced towards word endings. Obviously, this is a language specific, and our experiments were held on English language. So we embedded our observations explicitly on a speech pronunciation dictionary, and we have curated a Singer adapted version of it. And we used that Singer adapted lexicon in lyrics transcription experiments. We have observed consistent but marginal improvements. If you'd like to check the results, please copy and paste the title of this slide, because I didn't want to include a lot of numbers to cause any further distraction. So in our most recent paper, it's called the MIP-Frontiers. It's a multistreaming acoustic modeling for lyrics transcription. We try to answer both of these questions, if it's possible to obtain a single acoustic model or a cross-domain model, and also try to apply the latest state-of-the-art to lyrics transcription. I'd like to talk a little bit about the multistream architecture. So multistream time delay neural network architecture is actually the state-of-the-art neural network architecture for the DNN-HMM based ASR. Time delay neural networks are essentially one-dimensional convolutional neural networks where the convolution is applied on the time domain with a dilation rate greater than 0. So instead of convolving consecutive frames, we convolve frames dilated on time. A single stream architecture can be seen on the leftmost image, and the time delay blocks are highlighted with this dotted rectangular shape. In the multistream architecture, which is inspired by how human auditory system processes acoustic information in multiple resolutions. In this architecture, there are multiple streams of time delay blocks are included which operate in parallel, where each stream has a unique dilation rate, However, this architecture has identical structures for each stream in terms of hidden layer dimensions and number of hidden layers. So we compacted this architecture where each stream has a unique structure in terms of these parameters. The second method we proposed here was to develop a cross-domain model. So usually lyrics transcribers trained on either a cappella singing or polyphonic recordings or specifically DAMP or DALI dataset. As a simple but effective approach, we merged both of these datasets and then trained a single model to obtain a cross-domain model. And finally, we proposed to use music-informed silence modeling usually in speech recognition. There are a set of phonemes that are used as target classes, which can be seen on the right, that is for the English language. And in addition, there is a silence phoneme inserted in the set of classes, which is used to represent the non-vocal instances. In addition to this, we also insert another silence phoneme, which we refer to as music phoneme. We explicitly embed this information prior to training through tagging the lyrics, through explicitly including these silence tokens at the beginning and at the ends of each lyrics line. And then we exploited the fact that we know DAMP data is only a cappella and the data is only polyphonic. And then both of these method 2 and method 3 led to considerable improvements. We were not only able to maintain performance across different domains, but we were also able to achieve performance improvements. On the other side, music from silence tagging or silence modeling was mostly effective for polyphonic case, but not so much for a cappella case. So yeah, the lower the error rate is better, again. So the final results in this paper, we included our mystery net with the other methods that we proposed. Note that in this paper, we have also introduced a new dataset for benchmarking polyphonic lyrics transcription, which is a subset of the DALI dataset, and the annotations are manually verified, which is the largest evaluation set for lyrics transcription with the highest musical variability, while we maintain singer's gender. And this data can be retrieved via the tutorial we provide at this link. So just to summarize these results in this table, if you just take a look at the two bottom lines, the second line from the bottom is the state of the art that is reported in the literature, and the bottom line is the results that we reported in that paper. So as you see, especially for the polyphonic case, that's a substantial improvement. And now this is the state of the art by large margin. For the information, the other state of the art for the monophonic recording is our previous publications. So our last research question, DNN or HMM models, whichever is more suitable for this task. For the DNN-HMM model, we used our mystery net, and for the end-to-end model, we used a pre-trained acoustic and language model trained on the large benchmark speech corpus, Libre speech corpus. We fine-tuned both the acoustic and language models on the DAMP dataset, and we used the transformer architecture for that. The best results for both of these methods are similar, comparable, although the DNN-HMM model is still better. So the best results for the DNN-HMM approach was achieved through training a model solely on singing data, whereas the best results were achieved for end-to-end models through transfer learning or fine-tuning. So first we need a very good model trained on large speech dataset, and we fine-tuned it on singing. Note that transfer learning did not work quite well for DNN-HMM models. On the contrary, the end-to-end model trained solely on singing data performs absolutely horrendously. It's an interesting observation. So I'd like to ask A or B question for everyone. Whichever do you think is most suitable in this task? Just maybe raise a hand on Zoom. Do you think DNN-HMMs are more suitable for lyrics transcription or end-to-end models? Anyways, well, it's a really hard question to answer, but let me give my input on this. Let's go through the pros and cons for each method. Well, it appears that DNN-HMM models are suitable for low resource scenario. They come with better performance, and they have multiple independent blocks that can be individually optimized. And we have tested this model on real-world data. On the other hand, neural networks are not fully exploited, and there are lots of complicated data processing steps such as alignment, building phoneme context trees, etc. On the other hand, having multiple independent building blocks is not necessarily a good thing, because optimizing a single block does not necessarily lead to a global performance improvement. For this reason, fine-tuning is difficult, and this method requires a strong theoretical background. For end-to-end models, we don't need a pronunciation model, which is the feature of them that makes them most attractive. They're easier to train, minimal data processing involved. Neural networks are exploited to its fully extent, and they are more modern and flexible. On the other hand, they require very large training data sets to be able to get good performance. They have high memory requirements on the GPUs, and we have not tested this system on real-world data yet. To summarize our contributions, we were able to achieve the state-of-the-art in ALT, in lyrics transcription, across all benchmark datasets. This is especially true for polyphonic recordings by a large margin. We proposed a number of novel training approaches and novel neural network architectures. We introduced a new evaluation set, which is the largest in research. And through these contributions, we are benchmarking lyrics transcription research for both DNN-HMM and end-to-end based approaches. So I'm going to show a few examples. The first one is a monophonic example, and I hope everything goes well with the audio setting. Okay.
It's a little bit funny, this feeling inside. I'm not one of those who can easily hide.
So it looks pretty good. It was actually 100% accurate in this case, and as you see, it was able to model longer vowels. So yeah, we were actually quite happy to see this result when we first had it. And now I'm going to show some polyphonic examples, but bear in mind that the examples that I'm going to show do not necessarily represent my music taste. Yeah, let's have a listen to those.
Maybe you love me, but you're under the sun and beyond it. And it's so easy to lose the words and
So as you see, the upper row is the ground truth and the lower is the hypothesis. The wrong words are highlighted with red. So another one, this is a hip-hop song.
People dog LeBron till LeBron show up. When he steps on the pink, then they guards go up, scars go up, all the applause go up, and everybody in the whole damn club goes nuts.
This result is impressive. That's good. So another one. In this example, I'd like you to focus on the very end of the sample, and I guess you'll have an idea what I'm talking about.
To help you see, our love is rolling down so easily.
So our lyrics transcriber was attempting to transcribe the percussive sounds, which is unintended, and that's not my PhD thesis. So obviously, you know, we don't claim that we have solved this problem. We haven't solved the automatic lyrics transcription problem. There is obviously still large room for improvement. And in our opinion, and based on our previous experience, the performance improvement can be achieved through data augmentation or exploiting the available data to its greater extent through semi-supervised learning or representation learning methods. Also, we have to inject more music priors in this whole pipeline, such as leveraging rhyming information, and also multilingual lyrics transcription is an interesting research field. Having a multilingual lyrics transcriber would be actually commercially impactful. Also, there are still music-specific challenging cases, such as brutal vocals, like in death metal. I actually tested my system and it fails completely. Opera singing is another challenge, and also we have a lot of custom words in lyrics that we do not see frequently in natural speech. I'll give an example about that, such as this sample here.
I'm chasing highs.
So it's a little bit ambiguous how to model such instances, but that's also a future challenge. And our outcomes, research outcomes, well, within the context of lyrics transcription at least, we were able to publish 5 peer-reviewed papers in top conferences. All of our lyrics transcription training software is open source and in GitHub. We have introduced a new evaluation set, again, the largest in research so far. And we were able to develop, through our collaboration with Emir, we were able to develop the first commercial application of automatic lyrics transcription technology, which will be released in early 2022. Maybe you can have a screenshot and then copy and paste that YouTube link. and that's my email address, and this is the references. Thanks for your attention.